All right. This new PowerPoint is trying to explain a little bit better why the 3D subshell comes later than you would expect it to. So Hund's rule, orbital diagrams, valence electrons. Allegedly, this is review. And I'm going to claim that yes, this slide is review. Sublevels or subshells are made up out of orbitals. S-type subshells have one orbital, P have three, D have five, and F have seven. You're going to have to always remember that order. S, P, D, F. 1, 3, 5, 7. Each orbital can hold 2 electrons. So 2, 6, 10, 14 electrons. Aufbau is a German word. I don't know if it's someone's last name, but it means we always begin with the innermost, lowest energy level and work our way out from there. That's called the Aufbau principle. You don't move on to a higher level until the current one is completely filled. There is occasionally an exception to this rule in a small way, not in a big way. This one diagram is a great visual to try to make it clear to you the slightly unexpected order in filling out the subshells. So I want to draw your attention to the colored circles that represent subshells. The bottom left corner of the image, that navy blue circle, represents the nucleus of an atom. Surrounding it, the nearest subshell is principal energy level 1, subshell S, 1s. That is the lowest level energy level. The two black circles drawn on that subshell represent 2 electrons, one for hydrogen, one for helium. It is completely full. The next subshell, the next principal energy level is drawn in orange. It has 2 subshells, the 2s and the 2p. As you can see by counting the black circles, the 2s subshell is completely full. So is the 2p subshell. It's completely full with 6 electrons. That gets us through the first 10 electrons. In sort of a lightish greenish color are the 3 rings that represent the third principal energy level. But notice the odd characteristic that has a green 4s subshell, lower in energy than the 3D yellowish subshell. So while it's true that the third energy level has 3 subshells, S, P, and D, it's also true that the 4s subshell is slightly less in energy level than the 3D subshell. Hence, the order of filling electrons is to first fill the 3s subshell with 2 electrons, then fill the 3p subshell with 6 electrons, and before you fill the 3d subshell, you first fill the 4s subshell with 2 electrons. Then you move up to the 3D subshell, which can hold 10 electrons. The next subshell up from there is 4p, and it can hold 6 electrons. not well shown on this diagram, but there should be 6 electrons there. And just like before you rise up to the 4D subshell, you first encounter the 5S subshell. And so that's the order that you have to go. After you fill in the 4P subshell with 6 electrons, you can fill in the 5S subshell with 2 electrons. Then the 4D subshell with 10 electrons. Then the 5P subshell with 6 electrons. Then the 6S subshell with 2 electrons. Then the 4F subshell with 14 electrons. And finally, in this example for platinum, element number 78, the last 8 electrons fill into the 5D subshell. The rest of the subshells for the entire periodic table are shown as empty subshells. The long-form electron configuration for platinum is written in the bottom right text box. It matches the diagram behind it. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d8. How about that? Isn't that great? Now for Hund's rule. Hund is the last name of some chemist who studied this stuff, again, about 100 years ago. He represented each subshell with boxes for each orbital. So the S subshell always gets one box. It has one orbital. The P subshell always gets 3 boxes because it has 3 orbitals. The D gets 5 boxes, and the F gets 7 boxes. Each box can hold 2 electrons. Now, there's a rule, maybe it's called Hund's rule, that says you're not allowed to put an electron into any particular sublevel orbital. Let me rephrase that. You're not allowed to completely fill any given sublevel orbital until each orbital has been given 1 electron. I'll try to make that clear as we go to these next slides. So let's start off with, let's see what they do. For example, consider the element carbon. Carbon has 6 protons, and therefore neutral carbon has 6 electrons. And the order of filling them always begins with the small bag, the first one passed out, the 1s bag that can hold 2 electrons. In this slide, they use dots to represent electrons. You are not going to do that when you do your homework. When you see these empty boxes on your homework assignment, you are to use arrows pointing up or pointing down to represent the electrons each time around. That's because electrons can spin, and they can spin clockwise or they can spin counterclockwise. We use an up arrow and a down arrow to represent those 2 different spin states. In general, they always try to cancel each other out. So we want to show that cancellation by an up arrow and a down arrow together in one box. On this slide, they're just using dots. So now I have the configuration for helium, 1s2. The next shopping bag is another small bag. Lithium, 1s2, 2s1. Beryllium, 1s2, 2s2. Boron, 1s2, 2s2, 2p1. And now here's the example of what we're trying to explain that's written in the colored text. It says in a given sublevel, every orbital gets one electron before any orbital gets a pair of electrons. So this last electron for carbon, the sixth dot, does not go into the box that has a dot in it already. That would violate the rule. This last dot goes in an empty box. The empty boxes on a given sublevel are always filled with one electron first before any of them are allowed to get a second electron. Let's do another example. For oxygen, it has 8 protons. Therefore, neutral oxygen has 8 electrons. Let's go dot, dot, dot. Hydrogen, helium, lithium, beryllium, boron, carbon. This is the previous example. So where does the next electron belong? Oh man, I should almost call on someone and pose that question. Emmanuel, M.
Can you hear me?
Yes, I can hear you.
Can you give me 1 second?
1 second. All right, time's up. Now what? Where do I put the next dot?
Next dot. Box.
Alexandra, do you agree? Good, that is correct. This is Hund's rule. Before any box is allowed to have 2 electrons on a given sublevel, all the orbitals have to have 1 electron. And so now that each of the boxes has 1 electron, I can start to double them up on this sublevel. That is an example of Hund's rule. Okay, there's still more today. This is one way of representing the arrangement of electrons in an atom. It's a little messier because you have to draw the box, and then you have to draw the arrows pointing up or down inside the box. But for a chemist, it better represents the model in their mind of what that atom is doing. So it's helpful in that sense. And if you guys end up wanting to major in chemistry, then that's where this becomes useful. Okay, so with these boxes, an up arrow represents 1 electron, an up arrow and a down arrow in the same box means that box has 2 electrons in it. And just to toss out yet another name, another scientist, his last name was Pauli, he came up with the Pauli exclusion principle. Wow. And I'm not going to address why right now. Let's skip it. So, what element is this? Oh, vanity. Yes. What element would this represent? Well, there's a single box, and it's labeled 1s, and it has an arrow sticking up inside this box. So what element would that be? Oh my goodness. Saeed, rescue her. I said rescue her, child. Oh my goodness. Well, yes, that is hydrogen. Good job, guys. So there's three ways we can represent it. One is with the boxes and arrows. One is with this long form configuration, 1s1, 1s2, and so forth. There is a third way, and you don't need to know it for tonight's homework, so we'll defer that one. This should obviously be helium, 1s2. Lithium, beryllium, boron, carbon, nitrogen. So we're following Hund's rule that says you can't put two electrons in one subshell orbital until all the orbitals in that subshell have one electron already. Okay, they spread out. Because they have like charges, they don't really like being that close to each other, and they prefer to spread out. It's like this. I have 3 rooms. I have 3 students. We're on a field trip. Wouldn't you rather have your own bed before you had to share with someone else? Of course. And that's the thinking of these electrons as well. You give them a room with 3 beds in it, and you're going to have one guest in each bed until you need to double up. That's exactly the thinking of these electrons. So here's oxygen. Now they start to double up on the bed, and fluorine, and finally neon. Neon has a completely filled energy level. The entire first row and the entire second row of energy levels are completely full. Neon has no interest in giving up an electron, and it certainly doesn't want to open up a higher energy level to add an electron. So neon is a noble gas that is non-reactive chemically. The next energy level opens up with a small bag, a single subshell, the 3s. One electron into there makes it sodium. 2 electrons make it magnesium. Oh man, this thing keeps going. Following Hund's rule, next comes 3p, 1 electron in each of the 3 subshells. Whoops. And this is the last one they show. So aluminum, and you can see 1s2, 2s2, 2p6, 3s2, 3p1. But the boxes show how those electrons are spread out. We are not going to do this today, but this is coming your way. I'm displaying it for the moment, and I'm saying time to end this recording.